Hello everyone, I'm Arkaprova Dutta. Thank you for the Presision LOC for inviting me. So what I'm going to talk about is briefly on the project that I have done for my MS thesis under Dr. Priyanka Chaturvedi at IIFR, which is on the topic exoplanets around subgiant stars. So what are exoplanets? Basically, these are simply just planets which are revolving around stars which is not our sun. Till today, over 5,800 exoplanets have been discovered. Unlike the planets in our solar system, they range vastly. There are lava worlds. There are even planets which are in entirely a diamond. Also, there are planets which have been found around all different type of stars, include starting from M dwarf to even O-type stars. So this is a slide I just took from IISER. So this slide briefly describes the most popular discovery methods of exoplanets, starting with transit photometry, which is very simple. As the planet moves around the star, when it just comes before the star, the brightness of the star, as some of the light gets blocked, it decreases a bit, and we get a transit characteristics. So similarly, we can also detect the presence of exoplanet using radial velocity, where we see a tiny wobble of the star because of the movement of the planet, and they cause slight blue shift and red shift in the stellar spectrum. There are also methods like transit timing variations, microlensing, in which, because of the planet's movement, the light from the background star do get slightly distorted. There are astrometry and very recently very famous direct imaging. So stellar evolution is a very complicated topic, so I'm going to just go over briefly on it to give a background of the subgiant stars. So based on the initial stellar mass, a star evolves via different mechanisms. So stars which have initial mass close to our sun, ranging from 0.3 to 8 solar mass, they, after the main sequence turn off, they go into this subgiant phase. The more massive stars, they also go into the subgiant phase, but that in our local neighbor of galaxy, that the number is very low, and practically we don't find much exoplanets around that massive stars. So till this date, as I have mentioned in the earlier slides, the most famous surveys like Kepler, TESS, even now JWST, they have looked for exoplanets which are around main sequence stars, stars which are like our sun. But they mostly have ignored what happens when the stars do get slightly evolved and becomes a subgiant stars. So we tend to bridge this gap. Also, there is another motivation for doing this study is simply because these subgiant stars are slightly cooler compared to their evolved counterparts. So in this image, which is taken from this paper, this shows for different spectral type of the stars, what is the absorption lines. So when we detect planets using radial velocity methods, we use these spectral lines, and as the star gets more hotter, there are less number of these absorption lines. So if they are below 7,000 Kelvin, we can detect easily. Also, as there is a gap in the study, we can do the exoplanet demographic of exoplanets around subgiant stars, which will help us establish a baseline for any further studies which could be done on subgiants. So these are the objective of my project. Of course, it is to initially study all the existing exoplanets around subgiant stars. So even though Kepler and TESS targets main sequence stars, a total of 190 exoplanets, around 154 subgiant stars have been found out. So we do an initial demographic study on them. We try to do it uniformly and homogeneously. Also, the RV data from HARPS, Corally, like spectrographs are scattered. So we also try to propose an RV survey, which will be done over the next 3 to 5 years, and then compare all these data. So this is the first plot that I got. So this list, compares the subgiant stars compared to other type of the stars, which is mainly dominated by main sequence stars. So you can see a slight difference in this plot. There are very less number of smaller planets around close by region for the subgiant stars. This is also a sort of expected because these stars are slightly inflated. So for the uniformity and homogeneity of an occurrence rate, which is to get an idea of what the exact number of planets we would expect around these subgiant stars, we take a sample from TESS. We set a surface gravity limit of 3.5 to 4 log G with radius less than 3 solar mass. We get 788 confirmed and candidate for this occurrence rate. We then use openly available exoplanet detection pipeline, like Sherlock pipeline. Then we use for the vetting Triceratop, and then we use injection and recovery. So this process is actually quite computationally challenging. I'm using TIFR's HPC, but still, in the last 3 months we were able to finish the search and vetting for all of the 798 stars. But in this presentation, I'm only going to show occurrence rate for 45 stars, which are in this effective temperature region. So this is the occurrence rate of the exoplanets around subgiant stars. So there are two interesting things we see in this plot. One, we see almost negligible amount of planets which are small and close by. Also, if you look very carefully into the data, it varies from 0 to 0.03% occurrence rate. From the Kepler, when they did a complete occurrence rate study for the main sequence stars, they found it to be around 0.05%. So the planets that we are finding, or they are actually around subgiant stars, are much less in number compared to the main sequence stars. We also found two interesting examples during this process. This is one of the test candidates. So we find 8 complete transits from TESS, which all of them are double humped and consistently double humped. In the plot next to it, I showed the ground-based transit from South African LCO observatory. This is also double humped. This is still not clear why this is, but the consistency could be because there is a small planet with exactly same Epimedis. We also find this another candidate with an orbital period of 186 days, and we are currently following it up for radial velocity using the Paras 2 observatory in India. So the radial velocity survey that we propose is mainly taken from the Gaia data. So we take selected Gaia stars and use Lamos low resolution spectra to cross it, get an estimate of which stars are subgiant. And after removing the possible binarities, and as we can only get time in 1 to 2 meter telescopes like Paris and Tottenberg Landessternwarte. So we limit it to 11.5 magnitude of maximum of minimum brightness. This is the rough distribution, and this is only for the northern sky. This sample for southern sky is still in process of development. So this is the future aspects. I'm gonna briefly, I think I already have mentioned most of it. Another thing we plan to look at is, as I have initially mentioned, the radial velocity method uses absorption lines to calculate the radial velocity from the high resolution spectrum. But these subgiant stars are slightly more spurious and they are more active. So the 23 chromospheric lines which are used, we intend to study all of them for the 82 samples that we hope to get data from. And we also like to characterize the activity limits, and maybe hopefully now if we can find some of the lines which can be eliminated, then we can increase the precision of exoplanet detection around subgiant stars.
Thank you very much for sharing your work. Questions? Arkaprova,
yes.
Thanks for your presentation. Maybe I was not careful. I actually missed the real science objective of your work. So you are particularly looking at subgiant stars.
Yes.
And exoplanets around subgiant stars.
So
how do you define subgiants?
So subgiants are stars which have exhausted their hydrogen core, and the characteristic for detecting these subgiants are helium shell burning. So if you look into the even in the photometry.
Okay, I got it. So then my point is, in one plot, I saw that you are comparing subgiants with main sequence and giants. Am I right in understanding that?
Yes.
So why would you expect that subgiants to be? I can understand that main sequence and subgiants you are making some classification, but subgiants and then main sequence and giants, I didn't understand the control sample. So can you explain that?
So this is directly taken from NASA Exoplanet Archive. So what happens is around main sequence stars, there are 2 points. One, these stars are, which are main sequence, are comparatively less active. So we see less activity when we get the photometric data. So that makes one effect in the detection of the exoplanets, because when there's more activity, more noise, there is less probability of detecting exoplanets. Also, these stars are slightly inflated. So instead of having one solar radius, these are twice the size. So the transit method detects based on the radius ratio. So smaller planets would be less likely to be detected because the radius ratio would be much less in these cases. The second important point is that these subgiants, when they expand, most of the nearby planets, as we expect, should get engulfed because of the tidal interactions.
So that's what we're trying to see. Okay.
Yes.
The mass range of the subgiant stars?
So what we found so far, at the best case, they go till 2 solar mass. So we can only, you have to understand that we can only detect exoplanets to maybe 600 or 700 parsec apart from our Earth. So this is a limited region, and most of the stars in this region seems to be not that massive, at least in this section of the galaxy.
What is the population of the subgiant stars in that region?
From Gaia, we get almost 186,000 subgiants. Yes.
All are helium burning state.
They are all helium shell burning. Yes. Sorry, hydrogen shell burning, and the core is exhausted hydrogen.
Any more questions?
Thanks for the talk. I had two questions, if I may ask. Short question. So firstly, in the case where we're getting a double hump, that much, is it possible to do a spectroscopic study then to identify?
Yes, it's possible, but it's slightly difficult because this is a binary star. So Corelli took high resolution spectra for this star. They found 15 km per second radial velocity. That cannot be because of a planet. So it's possible to model these things, but you have to take significant number of high resolution spectra to model the binary and the planet. So getting time in telescope to do studies for binary stars, it's a bit difficult to get.
What I mean is that if we have, for example, spectroscopic data too, can we then identify whether there are two times or one?
From spectroscopic data, we can, but we have to take more number of samples. That's the problem, to get time in observatory. So it's easier to do photometry. So if we can actually get time in 2-3 meter telescopes instead of 1 meter telescope, then we can measure the transit much more precisely with much less error, and we can model it better.
Thank you very much.